All right, thank you very much for having me here. So in the email exchange organizing this talk, Volodya said, he lined something up, but he sent me an email that sounded a little bit like an apology that since it was not the geometric Langlands seminar, the talk would have to be finite. I wrote back, it's okay. I expected that it would end sometime. Then he wrote to me again and said that he had resolved the issue and the talk could now be infinite. So I brought a lot of material today. What I would like to do is, there's a particular mathematical object that I've been thinking about a lot over the last few months. I would like to talk about this object. Now, one thing I could do is, the very next slide here could be a definition, and then I could, state some theorems and maybe sketch some proofs. That's one way to organize a talk. And I think that in this particular instance, that would be a terrible talk, because the object that I'm going to talk about is not very interesting by itself. It's more interesting in context, or maybe I should say, it's not interesting what it is, it's more interesting what it does. So what I would like to do in this talk instead is, in the first part, just talk about that context. I would like to tell a story about a particular part of mathematics and an empty niche in this part of mathematics, and then an object that I'm going to tell you is going to fill that niche, and not tell you what that object is, but just how it, the role that it plays there. And then we can take a break, and anyone who wants to come back after the break, we can start with a definition, and then I can tell you why things that I said in the first part of the talk are actually true. And then we can take another break, and if anyone is still left at that point, we can prove it here. So that's my plan for this talk. So let's get started. So this is a talk about prismatic cohomology. So let me just begin with a little bit of background on this. The story really begins about 10 years ago. So let's say C is the p-adic complex numbers, and let's say X is a smooth formal scheme over its ring of integers. And about 10 years ago, Bhatt-Lurie and Scholze introduced a new cohomology theory for geometric objects of this kind. Constructed an invariant that they called A omega of X. And it's a cohomology theory that sort of interpolates between or generalizes a lot of previously known invariants and encodes information about how they are related to each other. And then in a follow-up paper, they introduced a different invariant called syntomic cohomology. These syntomic cohomology groups are invariants that occur as the stages of filtration on a tall K theory, and they're closely related also to this A omega X of their first paper. And more recently, Bhatt and Scholze reinterpreted these invariants using the language of prismatic cohomology they developed. So this theory originally, their original A omega of X, the name for it now is the prismatic cohomology of X, or the absolute prismatic cohomology of X. But the advantage of this approach based on prismatic cohomology is that it's now not restricted to X that are of this particular type, like things that are defined over really big fields. This is also an invariant which you can really attach it to any p-adic formal scheme, things that are like formal schemes that are smooth over ZP, which is going to be the case of interest in this talk. Okay, so now let X be some kind of p-adic formal scheme, the kind of thing that you can talk about the prismatic cohomology of. These cohomology groups have another interpretation, which was introduced independently by Volodya and myself and Bhargav. The prismatic cohomology of X can also be interpreted as the coherent cohomology of some other object, not X itself, but I'm going to denote it following. Bhargav gave a course on this last year, and his notation for this is X with a superscript prism. So that's an algebraic stack in a certain sense, footnote, not quite an algebraic stack in the sense of Artin, but it's a reasonable geometric object, although it's not a formal scheme anymore. And its coherent cohomology is the same as the prismatic cohomology of X. And in the case where X is affine, or it's the formal spectrum of a ring R, I'm just going to denote that instead it's by X prism, by R prism. And the main case of interest in this talk is going to be the absolute case, where R is just the p-adic integers. And in this case, there are some other notations for this object. Volodya called this sigma, and Bhargav and I called this the Cartier bit stack, W-cart. And I will probably accidentally lapse into using that terminology when giving this talk. So if I use the term Cartier bit stack, I mean this thing ZP prism. It's a geometric object whose coherent cohomology is the prismatic cohomology of ZP. Now, Volodya introduced an enlargement of this stack that has a similar relationship now not to prismatic cohomology, but to syntomic cohomology. So the syntomic cohomology can also be, that's an invariant of a p-adic formal scheme. It can also be thought of as the coherent cohomology of a certain auxiliary object. I'm going to follow Bhargav's notation again. He called this X syn. And this is an enlargement of the prismatization of X. It contains X prism as an open substack. And Volodya's notation for this in the case of ZP is sigma double prime. So what do these objects do for you? Well, let me just make a definition. So if X is a p-adic formal scheme, a prismatic F gauge is some kind of sheaf on this object X syn. Or maybe not a sheaf, maybe something like a complex of sheaves. And again, I'm mostly interested in the case where X is the formal spectrum of ZP, and then I won't say it's a prismatic F gauge on X, I'll just say it's a prismatic F gauge. So these prismatic F gauge form some kind of category, and you should think of this as the category of coefficients for the theory of syntomic cohomology. If you have a variety X, you can not only talk about the syntomic cohomology of X, you can take its syntomic cohomology with coefficients in a prismatic F gauge. So what are some examples? Well, let's say X is any p-adic formal scheme. That means there's a map from X to the formal spectrum of ZP. And this gives you a map between these, I think Bhargav called these syntomifications, between these syntomified stacks. And you can take the structure sheaf of X syn and push it forward to ZP syn. And that produces some complex, quasi-coherent complex on ZP syn, the prismatic F gauge. And if X is smooth and proper over ZP, then this is actually a perfect complex on ZP syn. So it's something that has coherent cohomology sheaves. And this is a very natural way to get prismatic F gauges. You get, in particular, coherent prismatic F gauges. So let me, and then what's the relevance of these objects? Well, the syntomic cohomology of X, you can think of as the hypercohomology of this ZP syn, this stack, with coefficients in that prismatic F gauge, which I'm going to call E sub X. So again, when X is nice enough, this will actually be a perfect complex. So it has coherent cohomologies. Let me say a little bit about that. So this stack, ZP syn, I'm not going to give the definition of it in this talk, but let me just tell you a few things about it. So it really feels like a three-dimensional object. It feels like something, well, which specifically is regular of dimension 3. And more precisely what that means, it's not a variety, it's a stack. But it means that there's a faithfully flat map from the formal spectrum of a ring, which is actually regular of dimension 3. And that number 3 cannot be made any smaller. So if you were actually on a scheme which was regular of dimension 3, you would have a good theory of reflexive coherent sheaves, meaning coherent sheaves that are the same as their double duals. So this implies in particular that the coherent sheaf is a vector bundle away from codimension 3. And there's a similar story on ZP-SYN. And these reflexive sheaves have a nice classification. They're familiar objects to a number theory. So there's an equivalence between the category of reflexive coherent sheaves on ZP-SYN and representations of the Galois group of TP on a ZP lattice, having the property that the representation becomes crystalline when you invert P. And I'm saying this is essentially due to Bhatt and Scholze. They express this in a different language, not in terms of prismatic F gauges, but in terms of prismatic F crystals. But it's essentially the same statement. And well, you can do this not just for ZP, you can do this, or you can replace QP here by other p-adic fields. So how can you think about this? Well, just an observation, reflexive coherent sheaves don't form an abelian category. Even vector bundles don't form an abelian category. And they sit inside a larger category of all coherent sheaves, which does form an abelian category. That's a nicer place to work. And so the way that you should think about this is that the category of coherent sheaves on ZP-SYN, it's an enlargement of this category of reflexive coherent sheaves, which has an interpretation in terms of crystalline Galois. So the notion of a Galois representation being crystalline, it's a notion for representations over QP. And if you want a good integral theory where you have you can talk about, for example, P torsion sheaves, and you want the collection of these objects to form an abelian category, then what you want is this theory of prismatic F. That's the thing that it does for you. And one of the nice things about this is that it's not restricted to working over QP or over ZP or even over the ring of integers in a p-adic field. It's something which really makes sense for much more general p-adic forms. And a consequence, I guess this is the number theory seminar. So one thing that at least some number theorists are interested in is Galois representations. And if you want to really understand crystalline Galois representations at an integral level, then you should at least be interested in this category of sheaves on Z. So that's a motivation for why you might want to understand the category of sheaves. But why does that mean that you would want to understand ZP-SYN itself? So this is some kind of an algebraic stack or algebraic interpreted loosely. So it's something where you can talk about its R-valued points where R is a commutative ring. So what does it mean to have an R-valued point? Well, let's say you have a map eta from the formal spectrum of a ring R into this ZP-SYN. Well, then you can pull back along that map. That gives you some functor from the category of prismatic F gauges, so they're sheaves on ZP-SYN, to the derived category of R. And in particular, you can do that to the prismatic F gauge that you've associated to a p-adic formal scheme X. So if you have some p-adic formal scheme X, you can form this prismatic F gauge that I call E sub X. You could pull it back along eta, and then you get a complex of R modules. And if you like, you could take the cohomology and get actual R modules that are some kind of invariants of this. And so the way to think about this is that this ZP-SYN, it's some kind of parameter space for cohomology theories on p-adic formal schemes. Every time you give a point of ZP-SYN with values in a ring R, then you get a cohomology theory where you input a p-adic formal scheme and you output R modules. So what are some examples of this? Well, let me give an example which is probably very familiar. So if you have a smooth formal scheme over ZP, you can talk about its de Rham complex. And you can take the cohomology of that de Rham complex. Let me take the cohomology at the complex level, meaning take the R gamma to get a complex of ZP modules. I'm going to denote that by dr sub x. And this is an example of one of the invariants that we can extract from the associated prismatic F gauge. This is the fiber of that E sub x that I defined earlier at a particular point of ZP-SYN. In fact, it's a point of the open subset ZP prism. It's called the de Rham point. I'll denote it by eta de Rham. So this is telling you if you want the de Rham complex of X, that's the fiber of E sub X at the point eta. If you want the de Rham cohomology groups of X, well, you take the cohomology groups of that complex. So this would, of course, be an extremely convoluted way of defining de Rham cohomology. De Rham cohomology is a much older invariant than the theory of prismatic cohomology and these fancy stacks. But let me mention a variant of this, Q de Rham cohomology. So now let's say X is a p-adic formal scheme, which is equipped with a system of étale coordinates, x1 through xn. Then associated to that system of coordinates, there's a deformation of the de Rham complex, which is called the Q de Rham complex. And the idea is it's something that you write down where you've added a formal parameter Q such that when you set Q equals 1, it becomes the usual de Rham complex again. And roughly the idea is the de Rham complex is defined in terms of differentiating. So every time the usual construction of the de Rham complex would tell you you're supposed to differentiate a function with respect to X, you replace this by the operation of taking the Q derivative, which means that you take f of qx minus f of x divided by qx minus x. And so now, elementary calculus would tell you if this was like a differentiable function of a real variable, and you took the limit as q approaches 1, then that would become the usual derivative with respect to x. And the idea is you write down that formal expression and you don't take the limit. You just think of it as a formal function of q. Now, this is a horrible thing to do. To give you a complex of sheaves on X, you can take the hypercohomology of that complex, but it's not really canonical at all, right? It highly depends on the system of coordinates that you chose. But so this is sometimes called Aomoto-Jackson cohomology. But Scholze conjectured that actually, even though the complex itself is horribly non-canonical, if you think of this as an object in the derived category, it's actually canonically independent of the choice of coordinates. And moreover, it's defined canonically enough that you can define it even when you don't have a system of coordinates by taking the local constructions and gluing them together. So this proved by Bhatt and Scholze as one of the original applications of this new theory of prismatic cohomology. So they interpreted this Q de Rham complex as a special case of the theory of relative prismatic cohomology. And in particular, they showed that as an object in the derived category, it's really well defined and independent of your coordinates. Now, this stack, VP sin, I said it's a parameter space for cohomology theories. It's sort of a parameter space for all the cohomology theories that you can extract from the theory of prismatic cohomology. And in particular, that includes this Q de Rham complex. So I told you earlier, there's a de Rham point of ZP sin, even of ZP prism. So that's a map from split ZP in. But that's actually the restriction to Q equals 1 of a more interesting map. So I'll denote that by eta Q. So that's a map from the formal spectrum of ZP double brackets Q minus 1 into ZP prism. So that's call that the Q de Rham point. And well, that Q de Rham point corresponds under the dictionary I described earlier to Q de Rham cohomology. If you take the prismatic F gauge associated to a smooth p-adic formal scheme X and take the fiber at this point eta Q, you'll recover the Q de Rham complex of X as an object in the derived category. So one way that we could say this more informally is that this prismatic F gauge E sub X, it knows about de Rham cohomology, but it also knows this band theory invariant, this Q de Rham cohomology, which is relatively new. Knows that de Rham cohomology has this special deformation. And question you can ask is, what else does it know? What other invariants can you extract this way? So let me give a partial answer to this. So first, he observes that the ZP star, the group of units in ZP, it naturally acts on this power series ring, ZP adjoin Q minus 1. That acts by raising Q to power. So if you have an element gamma in ZP star, then it makes sense to raise Q to the power gamma. And well, the Q-Duram complex, it's naturally not just a complex of ZP double brackets Q minus 1 modules, it has a compatible action of ZP star on it. Or another way of saying that is that ZP star, it doesn't just act on this ring, it also acts on what I call the Q-Duram. Now on the Q-Duram complex, you have this action of ZP star, but when you set Q equals 1, you get the usual Duram complex, and that action becomes the trivial action. And if you translate this into the language of these points of this prismatization, what I'm saying is that there's a commutative diagram of stacks. You can take the formal spectrum of ZP adjoint Q minus 1. I'm going to call that the Q line. So that's acted on by ZP star. You can form the quotient stack. That maps into ZP prismatized. Now, if you restrict that to split ZP mod ZP star, that's by setting Q equals 1, then that factors through the projection map to split ZP going in by the Duram point that I mentioned earlier. So this is a commutative diagram, and Vargo and I proved something about this, which is that if P is an odd prime, then for many purposes, you can treat this like it's a push-out square. For purposes of computing cohomology of things. So let me just give an example of one consequence of this. So if you want to compute the absolute prismatic cohomology of some variety X, and you're at an odd prime, well, there's just a simple relationship of this with the Q-Duram complex. Namely, the Q-Duram complex of X, first, we're at an odd prime, so ZP star is a topologically cyclic. So just pick your favorite generator of that group, gamma. And then look at the action of gamma on the Q-Duram complex. Now, when you set Q equals 1, that becomes the trivial action. So actually, gamma minus the identity is divisible by Q minus 1. And if you look at the map, which is gamma minus the identity divided by Q minus 1, that's a map from the Q-Duram complex to itself, the fiber of that map is what computes absolute Duram cohomology. So this is a strategy. If you want to know about prismatic cohomology in general, you really just need to know about the Q-Duram complex. You need to know about that action of ZP star, and you need to know that that action becomes trivial when you set Q equals 1. Everything else.
Just a moment.
Yeah.
To double check. Have you defined X?
What's that? In this talk?
Yes.
No, I haven't defined.
No, but no, of course not. But did you say that R gamma? So you didn't define
R gamma of X prism.
Yeah, and the important thing is that you shake not to push forward to CP prism, but just the cohomology. Yes.
Well, no, I mean you could. So it's a statement for any prismatic FH. You take a sheaf on ZP, or any prismatic crystal, really. You take a sheaf on ZP prism, and you want to compute R gamma of it. The claim is there's a fiber sequence where the other two terms are the value of the Q.
And this R gamma is called absolute. Right?
Yes. Yeah, exactly. Okay, so this is really the starting point for what I'm going to describe in this talk. So this talk is an extended meditation on this mechanism for computing absolute prismatic cohomology, or this mechanism for understanding prismatic crystal in general, just by looking at its specialization at the Q-Duram. So let me ask a few questions about this. So what if you're not interested in prismatic cohomology, but you're interested in syntomic cohomology, right? This is a story about ZP prism, but what about ZP sync? What if you're interested in the prime P equals 2? So then the theorem that I stated on the previous slide, that's definitely false when P equals 2. And this application of it doesn't make sense either because Z2 star is not topologically cyclic. And even if you don't care about those things, maybe can we understand better what's going on here? Is there some way of, maybe more geometric way of organizing the reduction of prismatic cohomology to Peter cohomology? And so for questions like this that I want to introduce a certain mathematical object, I want to introduce another stack, which I'm going to call F1 syn. And here's what it's going to do. There's going to be a comparison map from ZP syn to F1 syn. In particular, you can pull back along that comparison map. So sheaves on F1 syn, whatever they are, I'll tell you more about them later. That category of sheaves maps to the category of prismatic F gauges. Now, this map is not going to be very interesting. It's going to be very far from being an equivalence. The category of prismatic F gauges, that's interesting. It knows a lot of arithmetic, but the category on the left-hand side does not. It's a category which is in some sense arithmetic free. And another feature that this is going to have, I'm saying sheaves on F1 syn, it relates to prismatic F gauges. So it relates to cohomology theories on p-adic formal schemes, but it also relates to cohomology theories on schemes where P is invertible. Relates to things like p-adic étale cohomology of Z adjoint 1 over P. And so, as you might guess, or guess from my abstract, I want to suggest the heuristic that this is like the prismatization of the field with one element. Do not take this very seriously. When I refer to the field with one element, I really just mean it has these two features, that it's going to be somehow prior to any kind of arithmetic, and also that it's not going to have anything to do with any particular prime. And I don't mean to imply any relationship with any other notion of the field with one element. Really, this is just an unfortunate bit of notation that I started using because I needed to call it something, and I haven't thought of a better one. So at least for this talk, I'm going to continue to use it. Okay, so let me tell you a little bit about it and how it compares with ZP. So first, let me talk about ZP syn itself. So this is some kind of a stack, but it's really a formal stack. It's something that's completed in two directions. So first of all, it's p-adically complete, meaning it's something that maps to the formal spectrum of ZP. And so ZP syn has to do with cohomology theories, and this p-adic completeness has to do with a coefficient side kind of completeness. It has to do with cohomology theories where the output of the cohomology theory is some kind of p-complete ring. Now, even if you take this stack and reduce it mod p, it's still complete in a different direction. It's complete along a certain divisor called the reduced locus. And this kind of completeness has a different interpretation. It's sort of a geometry side completeness. ZP syn has to do with cohomology theories where the input to the cohomology theory is a p-adic locus. Input is something that has been p-adically completed as well as the output. So let me just say a little bit more about how this reduced locus is defined. So on this stack ZP syn, when you set p equals 0, I hopefully mentioned earlier, there's this line bundle, O of 1, curly O of 1, the Borel-Kissen line bundle on ZP syn. And actually, if I write O of n, curly brackets n, that means the nth power of this Borel-Kissen line. And when you reduce mod p, there's actually a global section of the p minus first Borel-Kissen twist. That section is usually called B of 1. And that is a defining equation for this reduced locus. The ZP syn reduced is the vanishing locus of both p and this element B1, which is only well-defined mod p. Now, another thing you can do is instead of modding out by B1, you can invert B1. Now, this doesn't literally make sense because the stack is complete along the locus where V1 is equal to 0. So if you invert V1 in the sense of taking the complement of the locus where V1 is 0, you'll get the empty set. But what I really mean by invert V1 is working with sheaves work up to isogeny with respect to V1. And if you do that, that sort of implements some kind of forgetful functor from the category of prismatic F gauges to the category of Galois representation. You should think of the left-hand side as some integral theory of crystalline Galois representations, and inverting V1 forgets the crystalline condition. And so we just suggest a heuristic way that you can think about this, which maybe you shouldn't take too seriously. But this completeness with respect to V1, you should imagine maybe ZP sin sits inside a larger geometric object that has a generic fiber that is the classifying stack of the Galois group. So it's like a formal model of this classifying stack. A sheaf on ZP sin in particular gives you a Galois representation, but it also gives you some kind of extra integral structure on it that corresponds to the crystalline. So that's a heuristic. But for this stack F1 sin that I'm going to tell you about, it's not just a heuristic. These kind of things are going to literally be true. So let me tell you some features that F1 sin might have. So first of all, this line bundle O of 1 that I mentioned, it lives on F1 sin already. The line bundle on ZP sin is pulled back from this line bundle O of 1 on F1 sin. And the section B1 that you see mod P, that also lives on F1 sin already. But unlike the VP sin, this object F1 sin that I'm going to introduce, it's not completed in any directions. It's not p-adically complete. It's not V1 adically complete when you reduce mod P. You can introduce those completions if you want, and we will want a little bit later, but you're not forced to. The definition already makes sense at an uncompleted level. And now, if you do choose to complete at the prime P, then it literally makes sense to invert V1, and you will literally get the classifying stack of ZP star. And the heuristic is that this comparison map that goes from ZP sin to F1 sin, well, heuristically, the left-hand side is some kind of a formal model for the classifying stack of the Galois group. The right-hand side is some kind of formal model for the classifying stack of ZP star. And this is some kind of formal model for the cyclotomic character. So let me give an example of how this plays out if you're interested in the cohomology of the Broyles-Kissen line bundles themselves. So first of all, there's always a map from the cohomology of ZP sin with coefficients in O of n to the Galois cohomology of QP with coefficients in the nth Tate twist. So this map, again, it corresponds to forgetting some kind of crystalline condition. But it's actually an isomorphism as soon as the Tate twist is 2 or more. And the right-hand side is something that you can compute using local classical theory. And it's maybe a little complicated, but rationally it's not complicated. Rationally it's very simple. The cohomology is concentrated in degree 1, and it's just a one-dimensional vector space over 2D. So that's what the left-hand side looks like as well. Now, what happens if you try to do the analogous calculations on F1 sin? Well, something similar, but it's going to be not about the Galois group. It's going to be about the group ZP star. Actually, there's a comparison isomorphism here, which is going to be an isomorphism already if n is greater than or equal to 1, at least if p is an odd prime. And, well, that the right-hand side there, the group cohomology of ZP star, that's something you can compute, not with local class field theory. You can just compute it. It's easy. That's a cyclic group. And rationally, integrally, you get something not too bad. And rationally, you just always get 0, as long as the twist is at least 1.
That's good.
Yeah.
So it looks like from this, the F1 sin depends on P.
F1 sin depends on P, right? So there's a, when I said it's sort of independent of the prime, that's geometry side. So I'm talking about like I fixed a P coefficient side that I'm interested in, although you could glue them all together if you wanted.
at this particular point, where does FP1 syn it's kind of a stack over ZP?
Yeah, so it's going to be a stack over Spec ZP in this talk, but that's just because ZP involves fewer symbols than Z localized at P. If you wanted, you could make it over Z localized at P. If you wanted, you could make it over Z by gluing all of the versions together. I'm not sure how natural a thing that is to do. Anyway, we'll get there when I actually define it. Okay, but this is one of the things it's going to do. This is what the cohomology of the Broadcast and line bundles is going to look like. And you'll notice that the bottom is a lot less interesting than the top. There is some cohomology corresponding to X between these chain twists in the category of Galois representations, but those are not visible among representations that factor through the cyclotomic. And so what do I want to say about this? So this stack, I told you at the beginning, it's not really that interesting a thing, right? You're not interested in sheaves on it for their own sake. The category of sheaves is actually going to be a pretty simple thing. But what's going to be interesting about it is that you can exploit it to study VP syn, which has a much more interesting category of sheaves. And so a strategy that you could pursue is to try to get information about prismatic F gauges by studying this comparison map from ZP syn to F1 syn. F1 syn, I claim, is something you can completely understand, and then try to also completely understand the fibers of this map, and then you'll completely understand everything. That's the, in theory. So what's an example of a way that things feel a little simpler? I mentioned earlier, ZP syn really feels like it's three-dimensional. This object F1 syn is going to feel like it's 2D. Okay, so definitions. What is F1 syn? Before I try to answer, let's just ask what the question is. What is a definition? Imagine you're a mathematician like me, and you have a stack in your head. You have another mathematician or a whole group of mathematicians, and you want to tell them what that stack is. So what language could you use? What would you try to tell them? So there's at least 3 different ways that you might try to communicate what that stack is. So one is to say a stack is something that has a functor of points. So to communicate to you what X is, I will tell you what it means to give a map from an affine scheme into X. What are the R-valued points? So that's kind of answering the question, what X is. But another way that you might try to communicate X is to describe not what its points are, but what its sheaves are. To say what it means to give a category, say what it means to give a coherent sheaf or a quasi-coherent sheaf or a vector bundle or something like that. And so this, in particular, is relevant for the kind of stacks I'm talking about, because the point of these stacks is that their categories of sheaves are interesting. They're a way of, the stacks are there to organize information about the category of prismatic F gauges, which is the object that you're ultimately interested in studying. And now a third way that you might try to communicate what a stack is in coordinates. Maybe it's a stack which comes to you as the quotient of a scheme by the action of a group. And then you'd specify the scheme and you'd specify the group and how it acts. Or that's if you get lucky. And if you're unlucky, maybe it's not the quotient of a scheme by a group, but it's the quotient of a scheme by a groupoid. And well, these stacks are kind of formal, so maybe you need to allow formal schemes, that sort of thing. So that's another maybe less satisfying way of describing a stack. So let me just give an example with this Cartier bit stack, ZP prism. It's something that we can describe from all of these perspectives. So I can tell you what its points are. An R-valued point of ZP prism is an invertible module over the bit vectors of R with a map from the invertible module into W of R that satisfies some non-degenerate ZP. I can tell you what its sheaves are. So a vector bundle on Z3 prism is what's called a locally free prismatic crystal. It's a rule which every time you have a prism A comma I, you assign a locally free A module in a way that is functorial. And another way is that you could give a presentation of this stack by writing down an atom. So anytime you have a transversal prism A comma I, that gives you a way of writing ZP prism as the quotient of the formal spectrum of A by a certain groupoid. And the particular groupoid that you take, well, it's the formal spectrum of B, where B is the coproduct of A with itself in the category of prisms. So this is a sort of coordinatized description that very closely relates to the Tanakian perspective by describing prismatic crystals by some kind of descent. And well, there's a very natural example of this, which is to take A to be the universal oriented prism. And in that case, you don't just get a description of ZP prism as a quotient groupoid, you get it as the quotient by a group action. The quotient of a certain affine formal scheme, whose coordinate ring is written right there, by the action of an affine group scheme, which is the units in the bit vectors. So that's a pretty concrete description, but the cost that you pay is that both that formal scheme and that group that's acting are infinite dimensional objects. And that's sort of an inefficient presentation, because I mentioned earlier that, well, ZP sin really feels three-dimensional. That open subset ZP prism feels like you've deleted the closed point. It feels more two-dimensional. And this sort of infinite dimensional presentation of it doesn't make it obvious that it's really two-dimensional. So you might want to not take something like the universal oriented prism. You might want to take some smaller prism. And this is something that we'll come back to at the end of the talk. Okay, so where would we go ideally in this talk? What I would love to be able to do is tell you what the stack F1 sin is in the most satisfying possible way. I tell you what an R-valued point is, and then I tell you why this is related to prismatization. I define a map from ZP sin into F1 sin. I tell you what it does on R-valued points, and then understanding that, we would analyze the fibers of this map, and then we would win whatever prizes we hope to win from this, give some applications. But I can't do that for you. So the problem is that I don't understand F1 sin as well as I would like to. In particular, I don't know how to classify its R-value points. I don't know how to describe it from that functor of points perspective. I can describe it from the other perspectives, and I will a little bit later. One way of saying this is I would really like to give you a definition, but all I can give you is a construction. And because I can't give you a definition, it's also hard to directly describe what the comparison map is. And it's hard to analyze the fibers of this map. Now, some of these things become better for a related construction, which is not about ZP sin, but it's about what happens when you adjoin a P through to unity. And when I was originally preparing this talk, my intention was to actually, at this point in the talk, make a left turn, and for the rest of the talk, just tell this story about when you have a P through to unity, which is in some respects much cleaner. But as I went through the process of preparing it, I don't think it's a good idea. So when I was an undergraduate, I took a music theory course. So one thing that a professor said at some point, which kind of stuck with me, is you have to learn the rules before you can break them responsibly. And so I feel a little bit like that here. I need to tell you more what the problems are before you would be able to appreciate why adding a P through to unity makes the problems go away. So I'm not going to talk about this cleaner story. I'm going to talk about the story for ZP sin and stuff. So how is this talk actually going to go? Well, I'm going to tell you what F1 sin is, but not in terms by giving its functor of points. I'm going to tell you how to write down a presentation of it. Give you a bad definition. I'll explain many of the features that I mentioned in the first part of this talk. We'll just witness most of those features. And then I'm going to explain why it's related to prismatization. I'm going to construct the comparison map not on ZP syn. I'm only going to construct it on the open subset ZP prism. And the construction of this comparison map is going to occur simultaneously with a description of what the fibers of this map look like. I'm going to construct it in a way that you can't possibly not know what the fibers look like. And probably I'm going to run out of time before I get there, though maybe not if the seminar is infinite. So I think this would be a good place to take a break. So when we resume from the break, I will just start defining the object that I've been talking about. All right, welcome back. So I promised you a definition. But more than that, I promised you a bad definition, and it came back anyway. So no refunds. So it's really a construction. Okay, so for any non-negative integer n, I want to consider the following ring, which I'm going to denote by B superscript 1. It's a subring of QP adjoin n plus 1 variables. And it's the subring, it's a homogeneous, sorry, it's a graded subring. So I'm going to tell you what it means for a homogeneous polynomial to belong to that subring. It's the condition that if you think of it as a function and you evaluate it on a list of p-adic units, you get a p-adic integer. So what are some examples? Well, B0. First of all, this subring, it always contains all of the variables, tau 0 through tau n. And in the case of B0, it doesn't contain anything else, just polynomials in tau. Let me emphasize, this is membership is a condition I'm writing down. That's for homogeneous elements. It's possible to write inhomogeneous elements that satisfy this condition where their homogeneous components do not. But if you've just got one variable, in that case, I'm not going to write the index. I'll just write it as ZP adjoin tau. And then a homogeneous polynomial is just a constant multiple of tau to the n. And the only way that can take p-adic units to p-adic integers is if the constant in front is a p-adic integer itself. But as soon as you have more variables, then there's more interesting things that can happen. So maybe the most important thing that can happen is that in the ring B1, you can take tau 0, raise it to the p minus first power. Now, if you take any p-adic unit and raise it to the p minus first power, you get something which is 1 mod p. So if that's true for tau 0 and it's true for tau 1, then the difference will be divisible by p. So here's an example of something with QP coefficients satisfying that integrality condition. And in some sense, this example explains everything else, although I would prefer not to articulate that just yet. Okay, so there are these rings Bn. And let me make an observation about this. So if you, first, the observation is essentially, if you understand B0 and B1, you understand all the other ones. So the polynomial ring on n plus 1 variables over QP can be written as an iterated tensor product, where you just consider adjacent pairs of variables, like so. And now, if you restrict to these subrings, then you have the same feature, that you can recover Bn just by taking a tensor product of n copies of B1 relative to B0. So this is something, I mean, it's not obvious from the definitions that I give you. You need to like get in there and write down a basis for these polynomial rings in order to see. Okay, but let's believe that. And now I'll tell you exactly. Okay. So first, let me observe that as n varies, these B sub n's actually form a cosimplicial ring, cosimplicial algebra over ZP. I'll denote that by B bullet. So if you take the spectrum of B bullet, then you get a simplicial scheme. And the lemma on the previous slide is the statement that that simplicial scheme is a groupoid in the category of schemes. And that groupoid presents for you a stack. And that stack I'm going to call F1 syn with a tilde. So concretely, well, remember B0 is just a polynomial ring in one variable. So the thing that's being acted on by the groupoid is the affine line. And the thing that plays the role of the groupoid itself is the spectrum of B1, which is, well, it is whatever it is. And I'll give you another way of thinking about it in a minute. But that's some groupoid acting on the affine line, and you form the quotient, and you get this object F1 sin tilde. That's not yet the object that I want to talk about. Remember, by construction, all of these rings are graded. That means that when you take the spectrum, you get an action of GM. GM is acting compatibly on every term in this groupoid, so it acts on the stack that's presented by this groupoid. And F1 sin, the object that I do want to talk about, is what you get when you quotient further by the action of GM. You quotiented out the affine line by this funny groupoid and by GM, which is just acting in the usual way. So that's this object F1 sin. So I promised you a line bundle on this object. And by construction, there just tautologically is one, because I've given it to you as a quotient of something by GM. Whenever something is a quotient by GM, there's a line bundle, and vice versa. So the presentation, F1 sin tilde, that's by construction a GM courser. That corresponds to a line bundle that I'll call O1. And if you like, that line bundle is classified by a map from F1 sin to BGM, which is just a map. F1 sin mod GM goes to spec ZP. Oh, and there was a question earlier, where do these stacks live? Everything is happening relative to spec ZP. Everything, all the algebras are ZP algebras. And here BGM is a stack over ZP. Okay, so what can you say about this map? Well, in characteristic 0, it's very easy to describe what's going on. So remember, each of these BNs sits inside polynomials of n plus 1 variables over QP as polynomials which satisfy some integrality condition. Now that integrality condition is automatic if there are no denominators. And any polynomial you can multiply by a sufficiently large power of p to make the denominators go away. So this inclusion map is an isomorphism after you invert p. And what does that mean? Well, that means that this F1 sin tilde that you got by, when you invert p, that groupoid that was acting on the affine line is just the equivalence relation where everything is equivalent to everything else. And when you form the quotient, you just get a point, which in this case, well, means spec QP because it happens only rationally. So the map from F1 sin to spec CP, that's not an isomorphism, but it is an isomorphism after inverting p. When you quotient by GM, this line bundle O of 1, it classifies a map to BGM that becomes an isomorphism after inverting. So that tells you what the stack is in characteristic 0. There's only one characteristic 0 point of this stack, and the stabilizer group of that point is GM. Nothing more to say. But now in characteristic P, it's more interesting. So what happens in characteristic P? Well, remember that this B1, it doesn't just contain the two variables tau 0 and tau 1. It also contains this expression, which is tau 0 to the p minus 1 minus tau 1 to the p minus 1 divided by p. So that means that in the ring B1, tau 0 to the p minus 1 and tau 1 to the p minus 1 are congruent modulo. So B0 has two maps to B1, which take the generator tau to tau 0 and tau 1 respectively. Now those two elements, tau 0 and tau 1, are not the same, but if you raise them to the p minus first power, they become the same element mod p. And what that means is that once you've set p equal to 0, this function tau to the p minus 1, it's not just a function on the affine line, it descends to the quotient. It descends to this stack F1 tilde as a function. Now it's on F1 sin, it's not a function, but it makes sense. It's a homogeneous element of degree p minus 1. So it makes sense as a section of the line bundle O of P. So the upshot of this whole discussion is that this gives you a well-defined element in H naught of F1 sin with coefficients in O of P minus 1 reduced modulo P. So I'm going to call that section V1. And now in characteristic P, this stack F1 sin, it doesn't just have one point. It has a point where V1 is not 0 and a point where V1 is 0. So let's first talk about the point where V1 is not 0. So what happens if we invert V1 in these definitions? So remember, V1 really it's some power of tau. So inverting V1 is like inverting tau. And to answer this question, I want to give you a different perspective on what this ring V1 is. So let me write O ZP star for the ring of continuous functions from ZP star into ZP, continuous with respect to the p-adic topology. And this ring has a natural filtration where fill n is functions that you can write as a polynomial of degree less than or equal to n, possibly with QP coefficients. And now saying that it's a polynomial in one variable, but now if you take two variables, tau 0 and tau 1, and form this expression, tau 0 to the n, f of tau 1 divided by tau 0. Well, since f has degree less than or equal to n, this will be a homogeneous polynomial of degree less than or equal to n. And the condition that f sends p-adic units to p-adic integers is exactly the condition that this element, this function of two variables is an element of V1. So what that's telling you is that this ring V1, it's just the Riesz algebra associated to this filtration on OZP star. And this, in this picture, tau 0 is what's playing the role of the formal Riesz parameter. And now when I said we wanted to invert V1, inverting V1 is like inverting tau. And that's like, you know, a Riesz algebra, inverting the Riesz parameter is like forgetting the filtration. What happens there? Well, first, this filtration that I mentioned, it's not exhaustive if you really work over, before you p-adically complete. That is, the union of these fill m's is not all continuous functions, but it's p-adically dense in all continuous. Any continuous function can be approximated p-adically very well by a polynomial. And in particular, that tells you that if you look at that inclusion of the union into OZP star and reduce mod p, it becomes an isomorphism. So if you take V1, which is this Riesz algebra, and you invert the Riesz parameter, then mod p, it just looks like you took OZP star and added a formal parameter, which is invertible. And then what happens? Well, remember this V1 was the ring of functions on some groupoid that was acting on the affine line. Now, when you invert tau 0, it no longer acts on the affine line, it acts on the punctured affine line. It acts on the copy of GM that you get by removing the point where tau is equal to 0. But then forming the quotient by this groupoid, what's acting now is just Z. The spectrum of V1 is now just ZP star as a profine, incarnated as a profinite group. It is any profinite group you can incarnate as an affine group scheme. And that's what's going on here. So F1 sin tilde in this locus, it just looks like punctured affine line mod the action of ZP star. ZP star is acting in the usual way by multiplication.
Sorry.
Yeah.
In this map, where you define this map, where does like elements like tau 1 go?
So tau 1 is tau 0 times the identity function from ZP star to Z. So there's an element in fill 1, which is like the function E goes to E. Yeah. Okay, so then, but then remember to get F1 sin, we were supposed to mod out further by the action of GM, which is also acting by rescaling. Now it's not rescaling by elements of ZP star, it's rescaling by anything you want. And when you form that quotient, you're going to get that sort of kills this A1 minus 0 part, and you just get a point mod the action of ZP star. So the upshot of this is that after p-adic completion, if you're willing to invert V1, you're just going to see the classifying stack of ZP star. That's what I promised you earlier. So I kind of said this when you reduce mod P, but it works just as well if you p-adically complete. So consequence is that if you're interested in the characteristic P points of F1 sin, and now you're interested in a point where V1 doesn't vanish, there's only one such point. And the stabilizer group at that point is a ZP star. Now what happens if you allow V1 to vanish? So there's a closed substack of F1 sin where P is 0, which means V1 is well defined, and V1 is also 0. So I'm going to call that the reduced locus. And well, F1 sin, remember, it's a quotient of the affine line by some groupoid acting. And if you look at that affine line, well, you're setting P equals 0, so it becomes the affine line over Fp. And then you're setting the P minus first power of the coordinate function equal to 0. So it becomes this spectrum of this local arc ring, Fp adjoint tau, mod tau to the P minus 1. Now I call this the reduced locus. That doesn't look reduced, but that's not the stack. That's just something that you quotient out by to get the stack. And the groupoid that's acting, that's actually a transitive action, so the non-reducedness goes away. Actually, this F1 sin reduced, it has the form BG, where G is some affine group scheme over Fp. And now you have to work a little harder to figure out what it is. And my evidence for the fact that you have to work a little harder is that you did it wrong a bunch of times. So staring at it, the natural guess for what you would get based on eyeballing it turns out to be correct when P is odd. The stabilizer group at the closed point is a semi-direct product of GM and a divided power completion of GA, where GM is acting, well, not by the identity character, but by the P minus first power of it. And this turns out to be wrong when P is equal to 2. Now, so take my word for it, because I'm certainly not going to do that calculation in front of you in this talk.
So what does the subscript P minus 1 mean?
So the subscript P minus 1 means the GM is acting on GA sharp. It's not the obvious action. It involves the first raising to the P minus first power on GM, then doing the obvious action. Okay, so there's this closed substack where P and V1 both vanish. We can formally complete at that point. And I'm going to denote that by F1 sin hat. And this is the interesting part, right? I've told you exactly what it looks like away from this point, and I've already told you it looks a little complicated even at this point. But near this point, it's kind of interesting. And that's also the place where ZP sin lands under this comparison map that I mentioned in the first part. Okay, so I told you what F1 sin is, or I've given you a construction of it. So that's the coordinate perspective. Let me tell you about the Tanakhian perspective. What are vector bundles on F1 sin? Well, first, something I've already mentioned is that when you complete at the prime P, there's an open substack that looks like B of ZP star. And if you were just interested in vector bundles on that open substack, well, those are easy to classify, right? They just correspond to representations of ZP star. And well, if it's a vector bundle, it's a representation on a ZP lattice, like pre-ZP finite. And so we could ask, what more do we need in order to get a vector bundle not just on U, but on this entire F1 sin? So one thing that has to happen, remember, F1 sin is a quotient of A1 by something, and that something includes GM. So there's a map from A1 mod GM into F1 sin, which means any vector bundle on F1 sin should determine there should be some associated filtration. So what are the vector bundles on F1 sin? I'll tell you when P is greater than 2, they're classified by the following data. So first you give a ZP lattice. You give an action of ZP star on it. That's what you see on that open substack view. You see a filtration, which is what you see when you pull back to A1 mod GM. And you see a compatibility between these two structures, which is that first ZP star acts in a way that preserves the filtration, but it's better than that. At the associated graded level, ZP star acts diagonally. On the nth associated graded piece, it maps by G, acts by G goes to G to the n. And well, I said this for vector bundles, there are related statements you can make for quasi-coherent sheaves and quasi-coherent complexes, at least up to P completion. But the analogous state, no, I said P is greater than 2. Definitely the related statements will be false when P is equal to 2. I don't know about the vector bundle piece. The fact that this is a sensible thing to do when P is equal to 2 is a relatively new piece of information. Okay, so where do you see structures like what I just described? Things with a filtration and a ZP star action that at the associated graded level behave like this. Here's one way that you could define it. Let's say X is a smooth formal scheme over ZP. You take the Q-Duran complex of X, this object that I mentioned earlier, and you equip it with filtration, where fill n is just a copy of the Q-Duran complex, but you think of it as having a Q minus 1 to the n. And well, this isn't quite the situation of the previous slide because this is almost certainly not a finite module over ZP, right? These things are like ZP double brackets Q minus 1 modules. But I mentioned earlier, there's an action of ZP star on the Q-Duran complex. And when you set Q equals 1, it becomes the Duran complex and action becomes trivial. And more generally, if you look not at GER 0, but GER n, so you take Q minus 1 to the n, the Duran complex mod Q minus 1 to the n plus 1, well, instead of the action becoming trivial, it becomes the nth power of the obvious character. And I just want to observe, this is exactly the structure that I mentioned in the first part of the talk, that you need to know about the Q-Duran complex in order to recover prismatic cohomology from it, or in order to recover the associated prismatic crystal.
Is it possible to go back to the previous slides?
Yeah. So this was the structure that I said was relevant for understanding the difference between Q-Duran cohomology and prismatic. Recover prismatic cohomology, this is what you need to remember about the Q-Duran complex. And well, there's a similar construction you can give for any prismatic crystal, not just something you can do for the prismatic FPH E sub X. You can take any sheath on ZP prism, pull it back to the Q-Duran point, and then give it this Q minus 1 adic filtration, and you'll get exactly this kind of structure. And well, what this is going to be interpreted as a little bit later is implementing the direct image construction along this comparison map. I told you ZP prism maps to F1 sin. So if you have a prismatic crystal, meaning a sheath on ZP prism, you can push it forward to F1 sin and get a quasi-coherent sheath. And that's something that can be described in terms of exactly this kind of data. So this was originally, this was for me the starting point, just like observing that there was a functor from the category of prismatic crystals to the category of exactly this kind of linear algebra data that seemed like it was kind of an interesting thing to look at. And then eventually realizing that that linear algebra data was organized by an algebraic stack. So let me mention another way, another place where this category comes up. So if P is an odd prime again, this category of sheaves on F1 syn appears another place in work of Bachman, Berkman, and Zhu. What they call the stable homotopy category of the field with one element. So the design, I don't think the details have appeared about this yet. But essentially, the idea is they wanted to decide some version of motivic homotopy theory, where instead of working over a field, you build some category that kind of has nothing to do with the arithmetic of any field. It should map to the motivic homotopy category. And well, that's a complicated thing because they're doing stable homotopy theory, but you can make it simpler by finding in there an object that corresponds to the Eilenberg-MacLane spectrum, and then look at modules over that object. So if you were doing ordinary homotopy theories, you take the stable homotopy category and you look at modules over HZ, you just get the derived category of abelian groups. And the claim is that the counterpart here is something roughly like this should be true. If you look at the HZ modules in their stable homotopy category, you should get the derived category of F1 syn. I say approximately because I don't actually know the definition of the right-hand side. And there's lots of things you could tweak in the definition. For example, was F1 syn supposed to be p-adically completed? Was it supposed to be V1-adically completed? There's lots of different variants of the category on the left-hand side, and I don't know which one they are. Okay, so while we're on the subject of homotopy theory, let me mention an unrelated other relationship that F1 syn has to homotopy theory, which is that it appears in this theory of the even filtration. So Hahn, Roxett, and Wilson have introduced a construction where you input a commutative ring spectrum R, and it outputs an algebraic stack, what they call the even stack of R. And in good cases, it's a mechanism that you can use to compute the homotopy groups of R. There's some spectral sequence where you start with the cohomology of that stack, coefficients in certain line bundles, and it converges to the homotopy groups of R. And observation, which was, I'm crediting this to Arpon Raxit now, but Sanoff this year, maybe Sanoff made this up. I learned this from Arpon. I was in the situation where I needed to communicate a stack to Arpon, and I gave him some complicated definition of F1 syn, and he said, oh, I think that's the even stack of J. And so at least if P is an odd prime, F1 syn comes from this construction. You apply it to a certain example of a ring spectrum, which is very natural in homotopy theory. In homotopy theory, you can take complex K theory. If you p-adically complete that, it has an action of ZP star by Adams operations. And you can take the fixed points and then take the connective cover, kill the negative point. So that's a ring spectrum called J, and the even stack of J is the subject of this lecture. Okay, so now I told you that this was related to prismatic cohomology, and I have not yet justified that at all. So what does any of this have to do with this ZP syn and ZP prism that I talked about in the first part of the lecture? But let me now state a theorem for you. There's a comparison map from the prismatization of ZP into F1 syn. In fact, it lands at the close point. It goes to F1 syn hat. And what's more is an affine map which is smooth at relative dimension 1. So that's a sense in which this F1 syn is somehow letting you simplify ZP prism. It's telling you ZP prism is 1 dimension higher than this more basic object. So something, I'm going to explain this later in the lecture. This extends to a map from ZP syn to F1 syn. That I'm not going to explain in this lecture. And let me warn you that the nice features of this map, that it's smooth at relative dimension 1, not true for the extension. But when you extend this to ZP syn, the fibers of this map are not schemes anymore. They're actually still stacks. But I claim it's still an interesting map to look at. And let me just mention, for these even stack guys, this was just obvious. if you don't, why was this even a question? So for at least if P is greater than 2, they have an explanation for where this comes from in the language of even stacks. And the short answer is there's a map from J into TC of Z after you p-adically complete. They actually, I've had them explain this to me. It's actually, they work hard for it too. It's not just like you take the even stacks of both sides and there's the map. You have to, okay, so I promised you another break. I think this would be a good time to take it. Anyone who wants to come back after the break, I can sketch the proof of this theorem, the construction of this comparison. All right, so remember our goal for the rest of the lecture is to prove this theorem. Prove that there's some relationship between the prismatization of ZP, which I gave you a bunch of definitions of earlier in this lecture, if you'll recall. Maybe I gave them very quickly. We've never seen these things before. And this F1 sin, which we've been talking about for a while. I claim there's a map between them, which is affine and smooth with relative dimension 1. In fact, we're going to prove something a lot more precise. So this is very closely related to some ideas of Melodia. He put a paper on the archive last year about a certain formal group that you can write down over ZP prism. So he observed that this line bundle, Borel-Kissen line bundle O of -1, actually appears as the Lie algebra of a one-dimensional formal group. I'm going to call it H hat because it's a formal group, and subscript Drinfeld because I want to distinguish it from another object we need to introduce in a minute. So over ZP prism, there is this formal group. Another feature is that this formal group has a section S, which vanishes on a divisor, a one-dimensional group, and that divisor is the Hodge-Tate divisor. And he asked a question in this paper, which is, does this formal group have a decompletion? Is it obtained from an affine group scheme over ZP prism by completing along its zero section? And the answer is yes, and this is very, very closely related to what I've been talking about. I think that Devin Murnham also has a construction of this decompletion, which may or may not be identical to what I'm going to describe. So let me tell you first the overall story. So what does this have to do with our map from ZP prism to F1 sin? Well, first of all, I told you the Borel-Kissen line bundle already lives on F1 sin. And the phenomenon that that's the Lie algebra of a formal group, that also already appears on F1 sin. On F1 sin, there's a formal group that I'm going to call H hat. And it's related to Melodia's group under this comparison map, which I haven't constructed yet. If you pull back this group on F1 sin, you'll get a group on ZP prism. Now, over F1 sin, it's just a formal group. But if you complete at the close point of F1 sin, then this formal group has a decompletion, which I'm going to denote by H. Maybe the notation is a little confusing. I'm saying, you know, if you put the hat on the F1 sin, then you can erase the hat from the H. Another thing that happens is this section of Melodia's group. If you think of that formal group as sitting inside its decompletion, well, so already what I've said means that that formal group has a decompletion because you can take H and pull it back along row. And now if you think of the formal group as sitting inside this other group, then that section actually becomes divisible by P. It becomes P times a section not of the formally completed group because it actually vanishes nowhere. And actually, that's the universal example of a nowhere vanishing section of this group. The section S tilde gives you an isomorphism from the ZP prism to that group scheme H over F1 sin hat with its zero section leading. So this here is telling you that there's a comparison, right? This is H with its zero section roof certainly maps back to F1 sin. And the fibers of that map just look like the fibers of H with zero removed. So those are smooth of dimension 1. Okay, so this is a picture, but I don't want to assume that anyone has read this paper. And I don't need all of the picture in order to explain the comparison map. All I need to do is first build you a formal group over F1 sin. I need to explain why at the closed point it has a decompletion. And then I need to explain why there's an isomorphism with ZP prism after you remove the zero section. And actually, that isomorphism is an isomorphism, so it can go either way. But the way the proof is structured, the isomorphism is actually, it's going to go from the right-hand side to the left-hand side. H minus a zero section is going to map to Z. Okay, so now we're really just going to get our hands dirty. Because remember, we only have access to this stack the way I've defined it by writing down some coordinates. And now we're just going to play some games with those coordinates. So first, remember, F1 sin starts life as the affine line, and then we quotient by some strange groupoid action. So let's first see what happens on the affine line itself. So the affine line, spec of ZP adjoining tau. What is the formal group supposed to look like when we pull back to here? I'm going to call it H hat sub tau to remind you it depends on a parameter tau. And so as a formal scheme, it's just the formal affine line, meaning it's the formal spectrum of what you get by adjoining one variable that I'm going to call x. And to make that a group, I have to tell you what the co-multiplication is. And the group law is given by x goes to x tensor 1 plus 1 tensor x plus tau times x tensor x. And now that co-multiplication is designed so that if you take 1 plus tau times x, that's actually a homomorphism from h hat tau to the multiplicative. That's a character on this group H hat tau. I'm going to call that character Q. And there's another way of writing the coordinate ring of this, which I think is going to really be a more helpful way to think about it. We're not adjoining a variable x. We're adjoining a variable q and making q minus 1 divisible by tau. That's what this formal group is. So this operation has a name in the world of formal groups. We started with the multiplicative group when you have the coordinate q, and then we did a dilatation with respect to the divisor tau equals 0, the affine part of a blow-up to make a new formal group. Okay, so that's a formal group on the affine line that you can write down. And now let me just observe that when tau is invertible, then this map Q, which remember is 1 plus tau times x, then that's Q minus 1 is also a coordinate. In other words, the map from h hat tau to GM is an isomorphism formal groups. And in that case, we could make ZP star act. Right? ZP star acts on the formal multiplicative group by automorphism, by raising the variable Q to powers. And ZP star also acts on the tau line by rescaling tau, right? That action of ZP star came up earlier. And I just want to combine them. I want to make, after inverting tau, I want to let ZP star act on the total space of this formal group, H hat tau, by an element E in ZP star multiplies tau by E, and it raises Q to the E tau. That's an action that you can write down. And now I want to study what happens to this action if I no longer require tau Q. In other words, then Q is not a coordinate anymore. I really have to use the coordinate x, Q minus 1 over tau. Well, let's try that. So let's rewrite this action using the coordinate x. So remember, E, an element of ZP star, x is Q minus 1 over tau. So that's supposed to go to Q to the E minus 1 divided by E times tau. And now we'll just do some calculating. So let's write that as Q minus 1 plus 1 to the minus 1 divided by E times tau. And then let's expand that using the binomial theorem. So that's a sum over all n. Since I subtracted 1 there, I'll just use n greater than 0 of q minus 1 to the n, e choose n, and that denominator e tau is still there. But now I've written it in terms of q. I wanted to write it in terms of x. So if I write this in terms of x, well, the coefficient of x to the n there, right, I have to multiply by tau to the n. Now, one of those taus cancels with the denominator, and what we're left with is the coefficient on x to the n. It's tau to the n minus 1 divided by e times e choose n. Okay, so we're going to stare at this formula for a long time and just read off information. But this is the formula for how x is supposed to transform. So let's remember, here's the formula. First observation, look at this 1 over e times e choose n. So that's a function of e. It's a function which is given by a polynomial of degree n minus 1. It's also a function which, on a p-adic unit, takes an integral value. Right? On a p-adic unit, the 1 over e you don't care about, and e choose n is a binomial coefficient. So that takes p-adic integers to p-adic integers. So that means that if you take this expression and you just add a formal n minus first power, some formal parameter tau, that's an element in the Riesz algebra of OZP star that we wrote down earlier. We can think about this as an element of the ring D1. And so what am I saying? If I take this whole expression where I've summed over n, I can think about that as a power series ring in a variable x over the ring D1. And what that means is that this action of ZP star that we have when tau is invertible, that would tell you that this formal group descends to the quotient by ZP star. That's not just true when tau is invertible. This formal group that we've written down on the affine line is equivariant with respect to the groupoid action given by the spectrum of D1. So descends to that quotient. Now, to get F1 sin, we didn't just quotient by that, we also divided out by an action of GM. That's much easier here. GM action just is encoding gradients on all of these rings. So we're gonna, the affine line has a standard action of GM. The coordinate ring is ZP adjoint tau, and we'll just give tau degree 1. And now, if I want to make GM act on this formal group, well, now I need to add a variable x, and to make that compatible with the co-multiplication, I have to give x degree minus 1. And if I give x degree minus 1, then this formula that I wrote down earlier is compatible with the gradient, meaning input x is an element of degree minus 1, and the output is also an element of degree minus 1, because minus n from the x to the n, and then n minus 1 from the tau. What does that mean? If this formal group descends further, not just the F1 sin tilde, descends to the F1 sin itself. Formal group there. Okay, let's steer a little harder. So I've explained one of the things I was going to explain. There's a formal group over F1 sin given by this construction. I've explicitly written down some descent data. But now the claim is it has a decompletion not everywhere, but at the close point. So first, this decompletion is visible on the affine line. Instead of over ZP adjoin tau, instead of adjoining x as a power series variable, you can just adjoin x as a polynomial variable. Get a scheme instead of a formal scheme. Now, the co-multiplication, remember, that's x goes to x tensor 1 plus 1 tensor x plus tau times x tensor. So that's always defined at the scheme level and makes this into a monoid scheme. It's not a group scheme in general, because if you write the formula for the antipode, then you'll see that you need a power series in x instead of a polynomial. It's only a monoid scheme, not a group scheme. But if you reduce mod any power of tau, it becomes, when tau is 0, it is the usual additive. And now something that takes a little bit of work to check. But let's write this formula again for what descent data that we're using to descend this thing from the affine line to F1 sin, given by this formula. So this involves a power series in X. So a priori, it's only descent data for a formal. But my claim is that if you stare at this expression hard enough and modulo any powers of p and tau, there's only finitely many terms in this power series. So it's not super obvious, but it's a very concrete statement. So what am I saying really? You look at 1 over e choose n. So think of that as a function on zp star. Function from zp star to zp. What I'm saying here is, if you only care about this function modulo p to the 1 million, it's a priori a function which is given by a polynomial of degree n minus 1, then you can make the degree much smaller than that. You can approximate it by polynomials of lower degree if you only want something which is congruent mod some high power p. But it's a concrete statement about binomial coefficients that you have to check to prove this lemma. But what that's telling you is that, remember, modulo powers of p and tau, that's what's going on at the closed point, right? The defining equations of the closed point are p equals 0 and tau to the p minus 1 is 0. So that's saying we have a decompletion of this group scheme over F1 sin. But now we want to study not that group scheme, but that group scheme with its 0 section removed. So let's think about that, and let's again start by analyzing that on the affine line. So if you remove the 0 section from this h tau, you get the spectrum of zp adjoint tau, and now removing the 0 section means this variable x, you make it invertible. So zp adjoint x to the plus or minus 1. Now this is equipped with a gradient that corresponds to an action of GM on the spectrum. But because this graded ring has an invertible element in degree 1, that action of GM is actually a free action. And if you want to form the quotient, it's just an affine scheme. And it's just the affine scheme that's given by the spectrum of the degree 0 elements in this graded ring. Now, an observation that's going to be important a little bit later is that if I only care about the degree 0 elements in this graded ring, then I didn't need to invert x, right? Like x, zp adjoint tau is already in non-negative degrees. X is an element of negative degree. So throwing in x inverse doesn't help you get down the elements in degree 0. The degree 0 part is the same as the degree 0 part of zp adjoint tau at x. And well, remember x, the thing I really want to call it is q minus 1 over tau. Q is an element in degree 0. Degree 0 part of this ring is just a polynomial ring on one variable, q or q minus 1 or whatever. Now this made sense over zp brackets tau, but that was kind of an accident, right? In order to see a group scheme here, we really ought to complete with respect to p and tau. And if we do that, well, completing with respect to tau is the same as completing with respect to q minus 1, because q minus 1 is a unit multiple of tau inverse. Q minus 1. Yeah, q minus 1 over tau is a unit. That unit times tau is q minus 1. So formally completing at the closed point is completing with respect to p and p minus 1. And now we see a familiar ring here show up. This is the coordinate ring of the q line. Okay, so that's a first approximation to understanding the formal group with its the group scheme with its 0 section removed. I did it not for the entirety, not for the stack F1 sin, but just for the approximation to it given by A1 mod GM. So now I want to do it better. I want to look at this presentation of F1 sin by a simplicial scheme and do that for every term of this simplicial. So over F1 sin hat, there's this scheme, which is H with its zero section removed, the relative scheme. And then I can pull that back to the nth term in my simplicial object. And let me call the pullback x of n. So let's try to understand what x of n looks like. We just did this when n is equal to 0. So what we saw is that when n is equal to 0, that x of n was the Q law, the formal spectrum of ZP double brackets Q minus 1. And the analysis in general is very similar. We'll see again that this is an affine formal scheme. It's the formal spectrum of a ring that I'll call A sub n. And A sub n has a concrete description. It's the degree 0 part of the graded ring that you get by adjoining Q minus 1 over tau to something, and then completing. The only thing that's changed is that instead of starting with polynomial ring and tau, you have to start with the ring B sub n that I defined earlier. Something that's an enlargement of a polynomial ring on n plus 1 variables. Okay, so that ring A sub n is whatever it is, and A0 is ZP double brackets Q minus 1. And now what's going on here, as n varies, these A sub n's form a cosimplicial ring. And when I take the formal spectrum, then we get a simplicial, well, not scheme, but formal scheme, which is a presentation of the object that we're trying to analyze, H minus its zero section. Now, what are we trying to prove about H minus its zero section? We're trying to prove that it's isomorphic to the prismatization of the. I'm actually going to prove something more precise than that. So I told you earlier a description of the prismatization of ZP. You take any transversal prism that you want, call it prism A comma I, then you get a map from the formal spectrum of A into ZP prism. And that's a faithfully flat map whose where the fiber product can be described in terms of the coproduct of A with itself in the category of prisms. And you can take your favorite prism there. And my favorite prism is the Q-Duran prism. And the claim is that that's exactly what's going on here. So I claim that you get this simplicial formal scheme as the nerve of the map from Q-Duran line, Q line into ZP prism. And therefore, we have two different simplicial formal schemes. One of them is presenting the stack H minus its zero section. The other one is presenting the stack ZP prism. That's a. Oh, so what do we have to do in order to prove what I'm claiming? Well, A dot, I told you what it is on the previous slide. It came to us just as a simplicial ring. But in order to see that it matches this description in terms of the Q line mapping to ZP sin, we would have to promote that to a cosimplicial object in the category of prisms. And we would further have to know that that was, well, specifically that what we see in degree 1 is just the coproduct of two copies of what we see in degree 0. Or more generally, what we see in degree n is a coproduct of n plus 1 copies of what we see in degree 0. But well, once you do the n equals 1 case, the other case follows 1. So this second part is just a concrete calculation. As soon as you explain why this is a cosimplicial prism, you get a comparison. And then the question of whether or not that map is an isomorphism is just a yes or no. So I'm not going to do the calculation. I want to focus on why there's a comparison map at all. So why is this ring A dot actually the underlying ring of a prism? Okay, so let's just recall what AN is from the previous slide. So you took this ring B sub n that I defined earlier. You join a variable x. You think of x as, say, Q minus 1 over tau, but now there's lots of tau, so pick your favorite, Q minus 1 over tau 0. And then that's a graded ring. You take the degree 0 part and you complete. That's how A sub n is defined. And now I just want to observe, we want to know that want to promote this to a prism. So the first thing we want to do is make A sub n into a delta ring. We need to equip it with the lift of Frobenius. And actually, there's something that we can write down before we pass to degree 0. This graded ring B sub n adjoint x has an endomorphism phi. I'm going to define it so it's just the identity on B sub n itself. And I have to tell you what it does on the variable x, so equivalently q minus 1 over tau. And it's going to do the obvious thing. It's going to raise q to the p power and do nothing to the tau. So it's obvious that there's a ring homomorphism with these properties. It's kind of told you what it is. And now it's not obvious that this definitely is not a lift of Frobenius on the graded ring itself, right? This is a homomorphism of graded rings. It preserves degrees. So it's not, the p power map raises degrees by p. So those definitely won't be congruent mod p. But the next best thing is to it, when you restrict to elements of degree 0, this is a lift of Frobenius. And what this comes down to, it kind of looks like it should be a lift of Frobenius when I tell you it's raising p to the p power. But it doesn't look like a lift of Frobenius when I tell you that it should be the identity on B. That sounds a little weird. The identity doesn't sound like it should be like the Frobenius. And unless you remember what the ring B looks like, right? The elements, homogeneous elements in the ring B, those are functions from a product of copies of ZP star into ZP that are integral. And the elements of ZP satisfy Fermat's little theorem that when you raise them to the p power, it's congruent to itself, mod p. And so that's also true for functions with values in ZP, and that's what goes into the proof of this level. Something very special about what the elements of B look like. Okay, so now A is a delta ring, and to make it into a prism, I need to select a distinguished element. But it's better than this, because A is a delta ring that has an element Q, where the Frobenius is raises Q to the p power. And then you can always choose a distinguished element by taking 1 plus P plus dot dot dot. And that makes A sub n into a prism, A sub n comma x. Now we're almost done, but note I said earlier, the construction I just described, I chose a Q. I chose a variable x. There were actually, that corresponded to a particular coordinate on our formal group. When I'm overlaying B sub n, there's actually lots of choices, right? B sub n receives n plus 1 maps from B0, and each one of those has its own preferred coordinate on the group H. And so what I did when I did this calculation is I selected the coordinate coming from the associated to the variable tau 0, and I did some construction. But that's a priori not good enough for our purpose. We don't just want to know that each A sub n individually has the structure of a prism. We need to know that those are compatible with the cosimplicial structure. This is functorial in n. And so why did they not depend on which of the taus that I chose? And the answer is that things that I did on the previous slide have more invariant descriptions in terms of the structure of the group C H. So how did we get this Frobenius lift on A sub n? It was given by first doing writing down an endomorphism of the coordinate ring of the total space of the group. That endomorphism was just the endomorphism that corresponds to multiplication by p with respect to the group structure. And this ideal I sub n is generated by bracket p sub q, q to the p minus 1 divided by q minus 1. Another description of that is that you take your coordinate x, you pull it back under the multiplication by p map, and you divide it by x. And well, that a priori you might think depends on the choice of coordinate x, but actually it doesn't, because it has a conceptual description. It's cutting out the locus of points of exact order p in the sense of that Volodya introduced many years ago. And we're done. Thank you. Yes.
At some point, you mentioned geometrically, this F1 thing should be thought of as not. So should be thought of as independent. P. Seems like your construction now heavily relies on P at least.
So F1, the F1 sin that I've been talking about, there's a P that's been fixed through this entire lecture. So the F1 sin certainly depends on P. But the F1 sin has this open substack, which is BZP star. So, you know, the part of the Galois, the version of the Galois group, what do I want to say? The étale fundamental group of Z with P inverted has a cyclotomic character, which means that anytime I have a representation of ZP star, I can pull it back to make an étale sheaf on Z with P inverted. So that's the sense in which something is independent of P. Like sheaves on F1 sin, they give you coefficients, not just for cohomology theories on p-adic normal speed, but also for étale cohomology with P inverted. Is that the answer to your question?
Some sense, but I still, well.
There's also the question of, like, can we
glue
the different F1 sins such as, but that you can, because in characters of zero they all look alike. Whether or not you should.
Oh, sorry. Well, in what sense do it look alike?
Well, okay. So the way that I defined it in this lecture is everything was over ZP, and the generic fiber was BGM now over QP. But I didn't need to be over ZP. I could have been over Z localized. And if I had done that, it would be BGM over Q. But I don't know if that's a good thing. It feels a little weird. Yeah.
So there like a even stat point of view on this relation between
I think you could. Right. I think this particular presentation of both of these things, I think everything is the even stack of something. So I would have to think a bit to say what it was the even stack of. But I suspect, yeah, you could probably, oh, sorry, if P is an odd you could probably phrase it in that language.
I think you abstract, you mentioned some applications with syntomic homology.
Yeah, I think that was when I was more optimistic about how long it would take to describe it. So I had two applications that I wanted to talk about. So one is to this recent theorem relating the category of prismatic F gauges to Fontaine-Laffey modules. And another is this paper about the valence and fiber sphere. And both of those are things that have natural explanations that involve the objects that I've been describing, but the explanations require more ingredients than the ones I explained. Like I explained why there's a map from ZP prism to F1 sin. I need the map from F1 sin. Sorry, from ZP sin to F1 sin in order to, you know, to say things about prismatic F gauges. That's where they live. And for the valence and fiber square story, I think that I need to discuss the story when you have a P root of unity, which I also haven't said. Well, yeah, I lied, or I over-advertised. Yeah, so there's an interpretation of what they're doing involving some of these ingredients. Yeah. I mean, maybe you can say a very brief word about it. For this F1 sin, I told you it has a map from A1 mod GM. That was syntomic from BGM. Now you also have ZP sin, which lives over here. You form the fiber product. And this means, like in a range of degrees, this kind of behaves like an isomorphism. I'll just say more words. Like, so this kind of tells you calculations that you do here are not so different from calculations that you do here. And BGM is a lot simpler than F1 sin, so that's a one-line explanation of the mechanism by which this helps. Like F1 sin, well, the thing that goes in this corner is probably not obvious from a point of view that doesn't involve the objects I introduced in this talk. Say very briefly. Okay, so take everything that I did in this lecture. Every time I mentioned ZP star, like in the definitions of the BN, I said, something's supposed to happen when a bunch of numbers are in ZP star. Write down a weaker condition. Not only it only has to hold when the integrality only has to hold not only when they're p-adic units, but they're 1 mod p. That defines another object that I'll call F1 adjoining zeta piece. And this receives a comparison map from ZP zeta piece. Yeah? And so one of the things that is challenging about this for me is I don't know the functor points here. And so it's hard to analyze the fibers of this map. And in particular, I really don't understand this object. But here you can kind of understand the functor points, and you can understand the fibers of this map. And so the fibers of this map are things that are very easy to work. When p is equal to 2, there's no difference. So when p is equal to 2 here, so there are statements that fail about like concrete descriptions of what the category of sheaves here look like. But there are statements that get better, which is like trying to analyze the fibers. Or yeah, maybe the way to say it is, this is complicated. When p is odd, this thing is simple and the fibers are hard. And when p is 2, fibers are easy, but the base is hard.
Slides.
Oh yeah, I'll send it to you.
I will.
Sure.
Let us send the speaker